Hello, everybody, and welcome to your Chapter 8, Section 1, Notes on Soil and Subsidence, or I have it listed here, subsidence and soil. Now, when we say subsidence, we mean the tendency to sink. When something subsides, it goes down. And so as you can see right here, the soil underneath this city has definitely sunk to the point where it actually creates what looks like almost like a bottomless pit. I believe at some point it becomes a cavern underneath there, so that's why it looks bottomless. But that soil has definitely subsided. By the way, before I go any further, I do need to apologize if I sound at all hoarse. It's because I'm fighting a cold, but I do need to get this recording in, so I hope you'll bear with me. Well, as is common for starting any chapter, we start most chapters with some sort of a case study. And in this instance, it's the city of Venice, Italy. Venice is known for having streets made of water, that is canals instead of actual asphalt streets. And it's very beautiful. I'm going to show you some pictures in just a second. But the one thing I want to point out to you before we do is that Venice, the city of Venice, is subsiding. It's sinking into the floor of the lagoon on which it's built. About 1.5 millimeters per year. That's about 2 times the thickness of your thumbnail, you might say. And it doesn't seem like very much to you, but if it happens consistently, then over several years, buildings are really going to move down towards the water. It is built on a coastal lagoon, and it's kind of protected from the ocean. It's not right on the ocean, but it's protected from the ocean by some barrier islands, very much like you might see at the Jersey Shore. But even so, it is still it's salt water that is in and around Venice, and as such, being kind of in close proximity to the ocean, it is very prone to flooding right there. So let me show you a few pictures of Venice. This picture right here is a very common one that you might see, maybe 2 star-crossed lovers or honeymooners right here in a gondola. That's what they call those boats. And of course, since there are no streets, on a boat or on a gondola is one of the best ways to get around the city. These guys that pull you around are called gondoliers. But you can see that the walls of the buildings go right down to the water level, and the foundations are just above, or in some cases even just below, the level of the wall. I visited Venice after my senior year in high school, and I remember it being one of the more beautiful cities that I've visited in Europe. And this is a very common sight that you might see as well, like a narrow canal right here, and people crossing over from one side to another on bridges. Very picturesque. Very people take very good care of their homes, and it just has that old Europe look that is just so pleasing to look at. Like I said before, I remember crossing over the canals several times on these bridges, and as you can see, you can't actually walk across the canal because it's water. There are a lot of these kind of arc-shaped bridges right here. Now, one thing I want to point out to you is right down here in the lower left, you can see that the water level is actually crested over this curb, and the sidewalk adjacent to the building is probably getting a little bit wet right in there because the water level is high enough. That's just something that you would live with if you live in Venice, periodic flooding, because as floods increase, the city itself is sinking as well. So those two things go hand in hand to create every year. Here is an overhead view of Venice, or at least most of it. There's an area over here, kind of off the page that extends out a little bit more. It's not quite this squarish looking, but this is for the most part the majority of the city of Venice. And one of the main features you can see is this S-shaped. It's called the Grand Canal. I think it's called the Grand Canal, as I recall. You can get much wider boats in here and go just about all the way through. And of course, there are minor canals, these little skinnier ones here and here that you saw in some of those other pictures, where you have little bridges that go across them. The other thing I wanted to point out to you was right here on the right. This is called Piazza San Marco, or the Plaza of St. Mark, I believe. And this has been the scene of many famous movies. It's this big plaza here, and then there's this tower that you may have seen as well. So this is the city of Venice. And so, of course, you might ask yourself, well, if it's built on all this water around it, then where do you start building the buildings? Well, building in Venice is built on a series of piles. Piles. Now, I don't mean like piles of dirt or piles of stone, but these things right here, these vertical things that look like telephone poles, are called piles. And what these two guys are doing is this thing is called a pile driver. It's a heavy weight. They pick it up and then just drop it down, and it hammers this pile into the floor of the lagoon. And if you get enough of them adjacent to each other, you make a surface that you can build a building on, which is fine if the soil underneath the lagoon floor is able to support it. And apparently it's not, or at least not as much as the Venetians would like it to. So this all goes back to the whole idea of soil, which is the topic of this chapter. Soil determines, or the kind of soil it is, determines how it reacts to environmental factors. So let's first define soil. What is soil? Well, it's earth material. It can also be biological material as well that can support plant life. All right, so it's not just rock. It's not just minerals and that kind of thing, but it has enough biological material in it that it can actually provide vitamins and necessities for plants. That's why plants tend to grow in soil. The other thing about soil is that you can remove it without blasting. That's what it says right here. Now, what we mean by that is, let's say bedrock. All right, you want to build a skyscraper and you have to build a deep foundation. All right, if you hit bedrock, you probably have to blast that out with dynamite. All right, because bedrock is considered part of the Earth's crust. But soil, you don't necessarily have to dynamite out. You can just dig it out with a shovel. And so soil is thought of as being kind of like the blanket on the earth. You can remove it fairly easily. You don't have to blast it out. One thing soil enables us to do is evaluate natural hazards. For example, the last chapter was on mass wasting. And we saw that mass wasting took place in certain areas because of how the soil was disturbed. So how is soil produced? Well, it's produced by weathering. Now, I have this underlined right here. Weathering is the breaking down of Earth's surface materials, rocks, minerals, and other things. All right, now, they're weathered two different ways. They're weathered physically by being broken down by the elements, wind and rain and freezing and thawing of ice. It breaks rocks into smaller pieces, but also broken down chemically as well. Acid rain, certain chemicals that are in water can dissolve certain materials of the earth and cause it to break down as well. Also, organisms can contribute to the breakdown of rocks. Earthworms and moles and organisms like that break apart rocks as they burrow through. So any time that the earth's surface materials are broken down into smaller pieces, we call it weathering, and the result is soil. Okay, so what determines how soil is actually made? Well, climate is one big thing. Remember how I talked about how wind and rain can contribute to the breakdown of Earth's surface materials. Topography, of course, are you going to have steep slopes or are you going to have very flat area? That determines how fast Earth's materials are broken down. The parent material, what was the material previously that it came from? Was it easy to break down? Was it not easy to break down? That plays a big part. Time, of course. All right, how long do you have? It seems like over time anything can be broken down, but certain things can be broken down faster. And of course, like I mentioned before, organic processes. Organisms in the soil do play a big part towards breaking it down and making it more fine, making it into smaller pieces. So if you were to look down, if you were to dig down through a layer of soil, like get a great big steam shovel and dig one big scoop out, you would see a series of layers. We call that the soil profile. And so all these layers are parallel to the surface because as soil is laid down, it is laid down in parallel horizontal layers. So these various different layers are called horizons, soil horizons. Now, each of these have different names or actually different letter designations, and those all correspond to different types of material that are in those layers. The designation O indicates organic materials, and that makes sense because that stands for O. That means decayed plants and animals that usually make up the top layer, because that's where plants and animals generally live. The A layer is mineral and organic materials. All right, so a little bit of organisms, but also minerals as well. All right, minerals are the kind of building blocks of rock. So you're starting to get some rocky stuff in here. E, zone of leaching with the A layer. Leaching means when one kind of material kind of is drawn out of another layer by water or other liquid processes. Like when something kind of leaks out, you might call that leaching. B layers, right here. Clay. Now, when we say it by clay is very, very small sized particles. All right. Iron oxides. You've probably seen that before. Iron oxide you probably know as being rust, right? So wherever you see reddish in the soil, it means that it's a B horizon right here, kind of reddish orange, that rusty color. And that means that it is kind of been leached out from another layer. It's kind of water is drained through and deposited in that B layer right there. Like I said before, these subgroups of B, clay materials, very, very, very small sized particles, and calcium carbonate, that's basically the same thing as limestone or anything that has kind of a that can react with acid is a calcium carbonate right there. So that's Bt and Bk. C layers or C horizons are parent material. That is rock that has been partially weathered. All right, so it's partially broken apart into these other more fine layers up here. But as you're getting down lower, you're getting into the less weathered stuff. And of course, R is your final layer where it is parent material that is not weathered. You might say it's like bedrock. So these are all the different horizons that can be found in a soil profile. As for color, well, we generally think of soil just being brown, but actually if you were to dig down and look across all those different horizons, you'd see that it takes a number of different colors. If you were to dig around in the woods where you would have O horizons and A horizons, that kind of leaf litter and stuff that's decaying on the forest floor, you'd see that it is pretty dark. We would probably call that humus, that really dark kind of organic-y stuff. The E horizon tends to be kind of whitish in color. The B horizon can be kind of yellowish brown or kind of reddish brown. And there's a horizon called K, which is almost white. So these actually do vary in color. The problem, however, is that color can sort of be misleading and not give us a perfectly accurate idea of what that horizon is. But these are just general guidelines right here. It can also indicate how well the soil is drained. If you've got well drained, and what we mean by aerated, it means that that air has been able to get into it. There's still air in the soil. Usually it's kind of a reddish. If it's poorly drained and kind of wet and soggy, soil tends to be a little bit more yellow in color. So we're going to mention this term aerated a little bit later, but it is just how much air has gotten into the soil. Think of it like this: if you have a faucet, all right, and so here's a faucet right here, and water is coming out. Right, water has, when it comes out of the faucet, it has all those bubbles in it because there's a thing on the end called an aerator. And usually it has kind of a screen in there that when the water flows through it, lots of bubbles form right in the water that comes out of your faucet right there. So aerated means having air in it. Okay, how about texture? Texture of soil. Soil can be very fine or it can be very coarse. I mentioned before that clay is one of the smallest types of soil particles. Very, very fine. It also means that it's kind of hard to dig. If you ever dug a ditch or a hole or anything in your backyard, if you're digging through clay, it's very difficult because it's very dense and the particles are very close together. Less than, 4,000th of a millimeter. Very small pieces. Silt is the next size up, slightly bigger. Sand, to be, sand size, from maybe a fraction of a millimeter up to 2 millimeters. And anything bigger than that we call gravel, cobbles, or boulders, anything bigger. But all those things can make up soil. So in the field, you just sort of estimate, is this gravel size, is it silt sized or whatever, but then it really isn't identified perfectly well until it's brought back to the laboratory. So when you dig up a handful of soil and you hold it, it tends to clump together in these kind of clumps or aggregates, and we call them PEDs. Peds. So all those little like nuggets of soil that are called clinging together, we call those peds. So if you were to go back to a lab with your handful or your bucket full of soil and analyze it and figure out exactly what percent the various different grain sizes consist of, you would probably evaluate it on kind of a chart sort of like this. This is usually graphs we look at are only 2 axes. This has kind of 3 axes. You have one axis right here that tells you the percent of silt, the percent of sand, right, and the percent of clay right here. So 3 different sized grains of soil. And so depending on what the percentage is of each, you will have some sort of a point in the middle right here that your soil would fall into. Is it silty clay? Is it loam? By the way, loam means kind of like a sandy dirt, probably that you would see near the shore. Okay, loam and all these different kind of brackets right here are different categories by which you would measure the texture of soil. As I mentioned before, the kinds of peds that you can get in soil can also vary as well. It can be granular, that is just little beads, kind of like sand. All right, it can be sort of blocky, having having sort of flat faces and maybe angular edges right there. Prismatic is kind of interesting. As you can see right here, it makes sort of almost like columns that stick together, that kind of hold together, and they have these kind of rounded tops right here, but along the side right here, you see what look like columns or like bundles of fiber sticking together. And also you have a texture called platy, and that means it looks almost like scales or flat plates that are clinging together that way. All these are different kind of textures that you can get in soil. As we said, soil is formed over time, and so therefore different kinds of soils are in different degrees of formation, different degrees of development. Weakly developed soil, all right, may only be a few hundred years to a couple thousand years old since its formation. All right, moderately developed soil can be maybe 10,000 years old, and well-developed soil can be over 40,000 years old, or even a couple 100,000 years old and older. So these various different kinds of soils have different degrees of formation and weathering of those earth materials that are in them. And so if we sequence soil from youngest to oldest, we call it the chronosequence. Chrono means time, all right, and so youngest to oldest, you got your time sequence right there. So what it does is that gives you an idea about the recent history of an area. And so you saw which areas are most recently active and which areas are have been active for a more long period of time. You probably know that there is not just soil and earth materials in soil, but also water as well. Water oftentimes makes up a big component of soil. So if soil is saturated, it means all the little all the little spaces in between the pieces, that is all those pores right there, the openings in between the spaces are filled with water. So if it were not filled with water, we would simply call it unsaturated. And so the moisture content of the soil is how much water is in it. And as water kind of moves through the soil and freezes and shrinks, that determines how much the soil can shrink and swell as seasons come and go. So soil really makes for a good means by which water can flow through. Almost all the water that you drink all the water that you ever drink has at one time flowed through soil. And so if the soil is saturated, the water it's just wall-to-wall water in between the pieces right there. And if it's unsaturated, it means there's some air on top, and the water would be on the bottom, forming what we call a water table. Or you might say the top level of the water that is flowing through that soil. All right, so here's a good example of the different kinds of interactions you would have right here. Here's all of our pieces, our solid pieces there, various different grain sizes, and water that is able to move in between the pieces, and air pockets can get caught in between the pieces. Ultimately, air tends to rise to the top because it's less dense. And so that's why the water moves down to the bottom and makes kind of a level of water that we call the water table. But this is what you would see if you were to zoom in on any one of those microscopic pieces of soil. Okay, so with all these different kinds of soils, different age, different contents, it requires that we develop a soil taxonomy. Now, what a taxonomy means is just a classification system, and soil scientists rely on this, but even more so, farmers and people who deal with landscaping and things that grow rely on that as well. They need to know what kind of soil they have, and therefore, and depending on what kind of soil they have, that determines what they can actually grow. Engineers classify soils as well, because after all, if you're building a building, the type of soil that you're building on is certainly going to determine what you can build. And it's based on the particle size, all right, so how big are the particles and how much organic material is in it. Now the next slide, that'll make more sense on the next slide. That is, the next slide is a taxonomy of soils, where it shows the different qualities of soil. So from top to bottom, right? Oh, I'm sorry, not the next slide. It's the next one. These are all different names of soils and the different benefits that they have, the different characteristics that they have. I'm not going to make you memorize all these, but these are all the various names: entisols, vertisols, inceptisols, aridisols. All these have different uses in the agricultural and the engineering fields. This is what I meant to get to next. So here you have, look at the top right here, you've got gravels, all right, very coarse stuff. And then you've got sands, and then you've got silt, and then clay down here at the bottom. And so as you move down, you go from coarse to fine, and you go to an increasing level down at the bottom of organic stuff. You may know that peat, P-E-A-T, that right there, is a material that's very low. You might think of it as very low-grade coal that they use and they burn in places like Ireland, where you have a lot of organic stuff that's breaking down. Obviously, you can't burn gravel, right? You can't burn sand, but you can burn things that have organic material in them, and that is peat. So as we go from top to bottom, it goes from coarse to fine, and also from low organic to high organic down to the bottom of this taxonomy right here. So the reason we need to concern ourselves with soil is the fact that it's really the foundation of our civilization. Anything you eat, be it plant or animal or otherwise, ultimately relies on soil to be formed in one way or another. And the problem is that agricultural systems that we've set up, not just across our nation but across the world, many of them actually serve to destroy soil. This term this phrase, mining the soil right there, what does that mean? Well, it's not like mining coal where you go down and dig it out, but when you do mine coal, it means you dig it out and you use it up and it's no longer there. Well, if you mine the soil, the same thing is true. You're using it at a rate such that it is not replenished, and so it's like you're taking it away and not enabling it to be replenished, to be reused. All right, so we do that in industry, but also naturally what happens is that soil erodes as well. When mineral and organic material particles are worn away by wind or water, right here, we call that erosion, when they're carried away. All right, so when soil material is removed, it's oftentimes it can be replaced, but if it's moved at a rate that it can't be replaced, that we say that's unacceptable, that can't happen. Because if it's being removed at a faster rate than it can be produced, then at some point that's not sustainable and it's just not going to be there anymore. Here's a picture right here of Washington State. And in Washington, they have lots of agriculture, especially in the eastern part of the state, agriculture and cattle. But as you see this hillside right here, you've got all these gullies that are contributing, and this valley right there is a valley because that used to be soil that was there, but has since been carried away. So that is soil erosion that has been washed downstream right there and is no longer available for this farmer to actually use. In urban environments, this is especially a problem. Because first of all, in urban environments, you don't see much soil anyway. It's mostly covered up by concrete and asphalt and in metal and whatever else is making up that city or that urban area right there. And as you put up buildings, generally what happens is vegetation is removed. And so that organic material that contributes to the soil, the layers of soil, is removed, and so the soil not only is covered up by stuff, but it also can't. It is not just covered up by concrete and asphalt, but it also can't develop any further because vegetation is taken away. So the only way we really are able to counteract this is to protect areas in urban environments and try to revitalize the soil. Where we don't have protection, this problem persists of soil just going away and no longer being able to function as soil does. Now, most of what we care about is the top layer of soil. In fact, if you were to plant a garden, you'd probably go to Home Depot or Lowe's and get some bags of topsoil. Right? What does that mean? Well, that means it's organically rich. It has a lot of broken down and decomposed plant and animals in there. And that's really what enable our crops to grow well. It takes a long time for it to form, between 500 and 1,000 years, to form just 2 inches, or about a little more than 50 millimeters of soil. So for agricultural land, soil forms at a rate of about, 5/100ths to 1/10 of a millimeter per year, so not very much. Gosh, if you think about it, a millimeter is about the thickness, like I said before, of your thumbnail. Okay, so 1/10 of that isn't very much. The soil doesn't form that fast. And so as we mine soil and as erosion wears away soil, you could have centuries of soil lost in a very short period of time. So there are various different ways that we measure how soil is lost, or the rate at which it's lost. Usually it's over a period of time, like we lose soil at X number of tons per year, that would be weight, or X number of kilograms per year, that would be mass, or X number of cubic meters or cubic yards per year, that would be volume. So we measure the rate of soil loss over a period of time in a couple different ways, but the rate really means how much soil is removed from a location within a certain period of time. And in some ways, we can actually predict how much soil is going to be lost. There's the universal soil loss equation, which we'll mention a little bit later, that can sort of help us predict how much soil is going to be lost and where, so that we can make adjustments to it. So that's the end of our first section of notes for Chapter 8. We're going to pick up in the next video with Section 2. So thanks for watching, and I'll see you on the next one.